Welcome to a lesson with Dr. Powell. Let's take a look at RSA cryptography. We're going to start with the set where all of our messages live. This is a small example. Now, if this number is large and is the product of two primes, it is highly unlikely that you can pick something in here and it end up not having an inverse. Most probabilistically, if this is big enough, everything will have an inverse, therefore it will be a valid message and live in here. Even if you don't know how 77 factors. So the public will know 77, public information. Knows 77. Because that is where our messages live. So in general, they'll know this. They'll know what n is, and in our case, n is 77. Okay. Now the public also needs to know one more thing. The public needs to know how to encrypt things. So what we're going to do is, let's suppose that we have, for encryption, let's take 13 as our exponent that we're going to decrypt by. So the public will also know 13. 13 is an exponent, and we can call it the encryption key. So in order to encrypt a message, you take something in this set, a message in this set. So let's suppose that we take as our message 19. So let's suppose 19 is our message. Okay, so 19 lives in here. It doesn't share any factors with 77. All right, and so to encrypt, we take 19 thought of as mod 77, so I'll put a bar for that, and raise it to the 13th power. And the solution to this will be the encrypted message. Now, 19 to the 13th power, it looks fairly ominous if you're not using modular arithmetic. However, in modular arithmetic, you can always reduce mod 77 at different steps and get a nice outcome. I won't work through the details right now, but if you raise it 19 to the 13th power, you will end up getting 61 bar, which again lives in Z mod 77Z. So the encrypted message also lives in this message set. So let's take 19, raise it to the encryption exponent, and get the encrypted message 61. Now, how are we going to decrypt this? Well, in order to decrypt this, we would need to know some information. We would need to know a decryption key. The decryption key should be private. The public should not know that or be able to find it out. However, one can find this if they know how large this group is. The multiplication group, where we take out anything that doesn't have a multiplicative inverse. So if we know that, we can actually find the decryption key. Why? Because Z mod 77Z, if we count how many elements are in here, and we'll explain that in just a minute on how we would do that, but there are 60 elements in here. That means that this has a nice outside multiplication structure of Z mod 60Z. Another way of saying that is that the exponents of this group live in Z mod 60Z. That's where the exponents live. So 13 lives in Z mod 60Z. And the decryption key is simply the multiplicative inverse of 13. So your encryption key is an exponent, and the multiplicative inverse of it is the decryption exponent. And the decryption key, so the inverse of 13, mod 60, can be written down as -23. But remember that this is living mod 60. So you could think of it as a -23, or you could think of it as a +37. So let's just keep it positive for now. So 37 is our decryption key. Okay, so that means if we take 19 bar, raise it to the 13th, we end up getting our encryption. Now to decrypt it, what we would do is we'd raise it to the 37th power. In modular arithmetic, keep in mind, there are ways of speeding this process up. And that is equal to, so if we do that and raise it to the 37th power, we end up getting, and going through, we should end up getting our original message, and we do. We end up getting 19 bar. So notice what's happened. We start with our original message, we encrypt it, we get this. Okay, now we take this and we raise it to the decryption exponent, and we end up getting the message back. Why does this work? Let's think. 19 bar raised to the 13th power, then raise that to the 37th power. That's the same as saying 19 bar raised to 13 times 37. But remember that the exponents live in Z mod 60Z, and these are multiplicative inverses in mod 60. So this just becomes 19 bar to the first power. So the encryption and decryption work nicely. All the while, if we can just keep the number 60 as a secret, we would be good. Well, how in the world do we keep this number right here as a secret? Well, the way we find 60 is by knowing how this guy right here factors. If the number is large enough, factorization is too elusive, and we don't know how to factor it. Therefore, we cannot ever figure out how many things don't share a common factor with that number. So let's take a look at that now and consider, how do we find 60 from 77? Okay, so we're looking for the numbers that share no common factors with 77. If we consider the group Z mod 77Z via the Chinese remainder theorem, this is isomorphic to Z mod 7Z cross Z mod 11Z. Notice this is because 77 factors is 7 times 11, and 7 and 11 do not share any common factors with each other than 1. So now, if we're thinking about multiplication is actually done component-wise over here in these groups, which means that, and taking inverses is also done component-wise, which actually tells us that in order to be in the multiplicative group, this component has to have an inverse, and the other component has to have an inverse. So the Chinese remainder theorem actually tells us this, that we have the same Cartesian product right here as we did up here, even for the multiplicative groups. Well, this is very nice because these are easier to figure out. And the size of this multiplied by the size of this will give the size of this, since we're using ordered pairs, taking things from here and here. And the combinations of that would be the how many things here times how many things here. Now 7 is prime, and so you just take out 7 from the list 1 through 7, and you have 6. So 7 minus 1. So for a prime, you just take 7 minus 1, you get 6. Now over here, you have 11 minus 1, and you get 10. So we have 6 and 10. And notice that 6 times 10 is equal to 60. We just successfully figured out what it was. Notice that the way to figure out 60, it was necessary to know how 77 factors. And the information of how 77 factors tells us what to include and what not to include and how to count how many things don't share any common factors with 77. Thanks for watching.